In this video, I'm going to give a paper summary on the paper Small-Scale Proxies for Large-Scale Transformer Training Instabilities by Mitchell Wortsman et al. From Google DeepMind. This is one of my favorite papers because it demonstrates how expensive LLM training problems can be studied affordably and prevented affordably, which is an awesome strategy to implement. I'm going to start with an introduction and overview. Then I'm going to talk about the instability metrics that they present. Then we'll dive into the main instabilities and how to mitigate them. The impact of other known interventions. We are going to go into the aspect of predicting instabilities, identifying new instabilities that are lesser known or not studied as often. Finish with some other analyses, and then we'll conclude. So I came away with these 8 takeaways. Number 1, which is the main one, which is that instabilities in large-scale LLM training are present in small-scale training, allowing for compute-friendly investigation. And this is a massive benefit for LLM research in general. Attention logit growth is mitigated by using QK-layernorm. Output logit divergence is mitigated by using auxiliary z-loss. Warmup and independent weight decay stabilize training. Scaling depth destabilizes training faster than scaling width. We can predict large-scale instability learning rates by extrapolating small-scale performance. The lesser-known gradient RMS collapse is mitigated with decreased atom W epsilon. And parameter norm growth is hypothesized to cause attention logit growth and gradient RMS collapse. Starting with the abstract, although the causes of such instabilities that happen at large scale are of scientific interest, the amount of resources required to reproduce them has made investigation difficult. In this work, we seek ways to reproduce and study training stability and instability at smaller scales. So if we can do this at a smaller compute budget, that's going to save us a lot of time and money. They talk about the 2 sources of training stability that are described in previous work, the growth of logits in attention layers and divergence of the output logits from the log probabilities. They measure the relationship between learning rate and loss across scales. They show that these instabilities that appear in large models are also appearing in small models when we train with high learning rates, and that the mitigations at large scale also are effective at small scale. They also look at other interventions that are more well known, and they are looking to see how it improves training stability. And then finally, they study a couple cases where we can predict the instability before they emerge by extrapolating behavior from small to large scale. So here is the experimental setup. I'll just highlight a few points. The total number of steps is 100,000 steps. The batch size is 256 with a sequence length of 512 with sequence packing. And their MLP hidden dimension is 4 times the embedding size. And of course, a lot of other details and a couple other details that I have not included that were in the paper as well. All right, so with that vision up front and with the goal in mind, let's dig into the first major concept, which is how are we going to understand instability and how are we going to measure it? And the way we're going to do that, there's twofold. We're going to do learning rate versus loss curves. We're going to analyze those, and then we're going to use something that they introduced in this paper called learning rate sensitivity. So to investigate how model instability emerges, it is useful to plot the relationship between learning rate and loss for models of different sizes. They introduce learning rate sensitivity, which measures the deviation in final validation loss from optimal when sweeping learning rate across 3 orders of magnitude. If a model fails to train at high learning rates, then LR sensitivity will be high. So learning rate sensitivity basically measures how much your performance drops when you move away from the optimal learning rate. Lower learning rate sensitivity is better. It means that your model trains well across a wider range of learning rates, so you don't have to find the perfect learning rate to achieve the lowest eval loss. You have some flexibility. There's some kind of, I guess, yeah, flexibility in terms of picking a learning rate. So the bottom equation is the actual equation for learning rate sensitivity. And in that equation, there's L star, which is the minimum learning rate that you can achieve when you're training your model across a range of learning rates eta. So the minimum loss that you can achieve. So eta is your learning rate. You're going from A to B. You're training some model based on eta, which is your learning rate, and you get some kind of loss. And the minimum loss that you get is your optimal loss, and that's L star. So L star, optimal loss, lowest eval loss achieved by a learning rate in the range A to B, inclusive. So if we look at the learning rate sensitivity formula, L is the final eval loss when you train with a particular learning rate eta. L naught is the loss at initialization, and so we're taking the minimum of L or L naught, and L star is the lowest possible eval loss when training across this LR range from A to B. So the main idea here is that we're looking at the difference between a given loss and the lowest loss achieved. And we're trying to minimize that distance. In other words, we're trying to find a training regime where different learning rates can still give us close to an optimal loss. We take the average of that difference between the loss at a given learning rate and the lowest loss overall. We take an average across the range, and that is our learning sensitivity value. Again, lower is better. They use these 7 learning rates from 3 eneg4 to 3 eneg1, and then if they're not using that, they explicitly mention that in the paper for a given experiment. A couple points on LR sensitivity. It is invariant to loss. So what that means is if the network consistently achieves random performance across learning rates, keyword being consistently, then LR sensitivity will be 0. We do not offer a solution to this and instead recommend that LR sensitivity should always be examined in combination with the LR versus loss curves, as we do in this paper. It is meant as a useful summary of the LR versus loss curves, not as a metric to optimize in isolation. So again, the key thing is consistency. If you're training a model with 7 different learning rates, and in each case the learning rate is terrible, but it's consistent, the LR sensitivity will be good. It'll be very low. But that says nothing about the performance of the model. So you have to actually look at the loss curves and look at what is the actual final eval loss. And then they also mentioned that if there's an intervention, for example, if you're taking the square root of the learning rate before passing it to the optimizer, then LR sensitivity is not useful because now you're changing the meaning of what the learning rate is. Okay, so that's what we're going to focus on. We're going to look at a variety of loss curves as learning rate changes, and then we're going to look at the learning rate sensitivity as the number of parameters changes in their experiments. And we're going to see how different instabilities, kind of what they look like on those curves, and then we're going to look at how different mitigations then look like visually on those curves. So the first training instability, the first of the 2 main ones, is the attention logit growth. So in the self-attention layer, the queries and keys are combined to compute the attention logits, z, where we take the dot product and divide by the square root of the head dimension. And then we pass that through a softmax to produce the attention weights, which are then used to combine the values, v, where we use matrix multiplication. So Degani is the main paper they reference, and they observed that the attention logits, z, became large, which they referred to as attention logit growth. And when the attention logits get too large, you pass it through the softmax and you get a bunch of 1s and 0s, or close to 1s and 0s. And so they call this phenomenon, this of the weights collapsing to one-hot vectors, they call that attention entropy collapse. And so to resolve this issue, they propose QK-layernorm, which applies layer norm to the queries and keys before computing the attention logits. So here is an example of what this looks like in practice. On the y-axis, we have max attention logit. On the x-axis, we have the training step. In orange, we have QK-layernorm equals false, so we're not applying that QK-layernorm. In blue, we have QK-layernorm equals true. So when we're not applying QK-layernorm, the attention logit value spikes up to 1,000,000 after 10,000 training steps. When we do apply it, the max attention logit value stays at 10. And then we can also see that when the attention logit spikes, when it goes past 1,000, enters that 10,000 range, that's when the eval loss really gets worse. We see this behavior in a 9 million parameter model as well as a 4 billion parameter model. So again, this is an example of how small scale models exhibit the same instabilities and mitigations as large scale models do. The difference is the small scale model in this case, we observe this phenomenon at a learning rate of 0.1, whereas in a large scale model, we observe it at a learning rate of 0.01. But this idea is that we can still detect these things at a small scale. So how do we mitigate this attention logit growth? We do so by implementing what's called QK-layernorm, and this is from the Degani paper that was referenced. So they observed divergent training loss after a few thousand steps. This instability was observed for models with around 8 billion parameters. It was caused by extremely large values in attention logits, which lead to almost one-hot attention weights with near zero entropy. So they applied layer norm to the queries and the keys before the dot product attention computation. So we get something like this. So X is the input, W is the weight matrix for the query, and WQ, and WK is the weight matrix for the keys. And we're multiplying the input by the weight matrix, passing that through the layer norm. Then we're performing the dot product, which is our matrix multiplication, and then we're dividing by root D, and then passing it through the softmax. One theme that we're going to see, and this is something they hypothesize later on in the paper, is that the attention logit growth is dependent on the parameter norm growth. So the fact that the weights of the query and the keys, the weights are growing is why the attention logit is growing, because we're multiplying these together and then passing it through the softmax. So when you multiply these large norms together, you're going to get larger values. So passing it through layer norm is sort of, standardizing and minimizing, I guess normalizing, not minimizing, but normalizing these values so they don't get too large. And this is a chart from the Degani paper. Without normalization, attention logits quickly grow to over 50,000 in magnitude, resulting in one-hot attention weights after the softmax, and subsequently unstable training losses and gradients. So the three charts of interest here is that after about 2,500 training steps, without QK-layernorm, the loss diverges. We can see that the maximum logit increases, and we can see that the attention weight maximum spikes up to almost perfectly 1.0. All right, so how do we visualize this in the experiments that they performed in this paper? So here we have our learning rate versus loss curves, and then below we have our LR sensitivity curves corresponding to number of parameters. So let's first make sense of what we're looking at here. There's obviously a lot going on, and it took me a minute to get familiar with these plots. So first off, we have two colors. The blue line represents situations where the QK-layernorm was implemented, and the orange lines represent where the QK-layernorm was not implemented. So that's the first thing. The second thing is we can see our 7 learning rates of interest. So here's 3 eneg4, 1 eneg3, all the way up to 3 eneg1. Next, we see that all these different symbols represent the number of parameters going from 2.4 million up to 1.9 billion. So here at the top, we have 2.4 million, and the very bottom, we have 1.9 billion. And as we would expect, the larger models are yielding a lower final eval loss. So that's kind of getting situated with the top chart. In the bottom chart, the LR sensitivity value is plotted on the y-axis, which spans 2 orders of magnitude in this case. And then the x-axis is the number of parameters from 10 million up to 1 billion. So what are we seeing here? So let's look at this 1 billion parameter model at a learning rate of 10 e neg 2. After that learning rate, our loss spikes up, right? It diverges and our training has failed. What happens when we apply QK-layernorm is that we get almost 2 more orders of magnitude of learning rate that we can increase and still have a close to optimal eval loss. So again, learning rate sensitivity, we want that to be low. And the way that shows up itself on these charts is that we want this sort of flat line. That's what we're trying to achieve in these plots. If we can get this sort of flat line, that means that across 2 or 3 orders of magnitude for the learning rate, we have similar optimal loss. And that's what we want. And the reason we want that is we want to minimize the number of hyperparameter sweeps that we're doing to figure out what's the best learning rate for our training. Well, in this case, 10 e neg 3, 10 e neg 2, 10 e neg 1, all of those are relatively sufficient. And that is saving a lot of time and experimentation to find something that's going to let you train your model in a way that it performs well, or at least in a way that it lowers the loss. Okay, so that was the first instability. The second main instability is the output logit divergence. So let y denote the model's output logits, which are used to compute class probabilities p via softmax, where p equals the e to the y over z, where z is the summation of the exponentiations. This instability occurs when the logits diverge and become very negative, as we're going to see in a second. This mitigation of this instability is what's called auxiliary loss, and it's called the z loss, and this comes from the Palm paper, where they say that this model is trained with the standard language modeling loss function, which is the average log probability of all tokens without label smoothing. We additionally use an auxiliary loss of z loss equals 10 to the negative 4 times log square z to encourage the softmax normalizer log z to be close to 0, which we found increases the stability of training. So that alone gave me a sense of what this was, but I had to look around a little more online, and I found this explanation in a Hugging Face notes document where they show us that this log z, this softmax normalizer, what they're talking about here, if we go back up here, is this log of the sum of the exponentiations of our output logits. So torch.log sum x, we pass the logits, and we get log z. We square that log z to get our z loss, and multiply it by a penalty weight, which is 10 to the negative 4, and then we add that to the regular loss that we calculate with cross entropy, for example. Here's what log sum exp looks like in the PyTorch docs. So we have an input x. We calculate the exponent of each value of x in that row. We sum it across the row, and we take the log. So it returns the log of summed exponentials of each row of the input tensor in the given dimension. So what does that look like? So here's an example of the output logit divergence instability. This is a 2.4 million parameter model trained at a learning rate of 0.1. So on the x-axis, we have our training duration, so it goes up to 100,000 steps. On the y-axis here, we have the eval loss, and on the y-axis here, we have the output logit mean. And we have 4 different markers that are of interest. The solid lines are where we are using the z-loss. The dashed lines are where we're not using z-loss. The blue lines are when we're using weight decay, and the magenta lines are when we're not using weight decay. So the first thing I want to look at is what happens when I'm not using z-loss and I'm not using weight decay. So I want to look at this dashed pink line, this dashed magenta line. So halfway through training, the loss diverges, it explodes, and training fails. And the reason it does that is because halfway through the training, The output logit means are collapsing or going, or I guess they're exploding in the negative direction and going, past negative 100. So when we do apply our z loss, so we go from dashed magenta line to solid magenta line, our training continues and it's relatively stable. There's a little bit of a spike here, but relatively stable throughout the duration of training. And the output logit mean, instead of exploding in a negative fashion down to negative 100 and beyond, the output logit mean plateaus at negative 20. So that's with and without z-loss and no weight decay. When we introduce weight decay, we get some benefit, right? So we go from about 40,000, instead of failing at 40,000 steps, we fail at maybe 70, 80,000 steps, but we still fail before we reach the end of training. And the reason we fail is, again, the same thing. The output logits are exploding in the negative direction. When we apply weight decay and we apply z-loss, then we get this situation here where, again, we're plateauing our output logit means. And so we have stability and we can finish our training. What does this look like across multiple scales? So again, we're going from 2.4 million, in this case, up to 150 million parameter models. If we look at the largest model here, again, in pink is no weight decay, and dashed means no z-loss. And we can see that at 10 to the negative 2 and larger learning rates, we have failed training and the loss explodes. When we go from our dashed line, no z-loss, to solid line z-loss with no weight decay still, we can see that we can go past 0.1 as a learning rate and we can still achieve stable training. So that's one benefit. We can use higher learning rates. So that's hopefully going to converge faster. And the second benefit is that there's a wide range of learning rates where we're achieving about the same loss. So again, we have low learning rate sensitivity. All right, so those are the two main interventions that were hard to study at large scale because of the compute requirements, but we can see exist at small scale, both in terms of the instability exists at small scale and the mitigation of the instability exists at small scale. And we can see that very small models like the 2.4 million or relatively large models like the 1 or 2 billion, the entire range are exhibiting the same behavior. So we are able to analyze and study these instabilities and mitigations at a much, much cheaper compute cost. So they take this a step forward and they say, okay, what is the impact of other known interventions on training stability? So they find that longer warm-up reduces learning rate sensitivity, so that's good, as does the independent scaling of learning rate and weight decay that was recommended by the original authors for that algorithm. And then they also find that scaling depth increases learning rate sensitivity, so it makes it worse, at a faster rate than scaling width. And we'll get to each one of these. So first known intervention is adding longer warm-up period. And that's what we're going to look at here. So the pink line here is a warm-up of 50 steps. The blue lines are a warm-up of 25,000 steps. The main thing in the LR sensitivity chart is that as the number of parameters increase, having a larger number of warm-up steps reduces the LR sensitivity by an order of magnitude. So that's really positive. And we can see that it's a little busy in the chart, but we can see, down here in the blue circle that I've highlighted, we have our warm-up of 25,000. And if we look at this bright pink line here, we can see that that explodes at the same learning rate that we still have some stability. So we can see that as the number of parameters increases, we can train for larger learning rates and we can train for a wider range of learning rates and still get optimal loss. So known intervention, longer warm-up. Next, parameterizing weight decay independently of learning rate reduces LR sensitivity. While this was recommended by the original authors, it's not common practice in how it's implemented in PyTorch. So recall that the unscaled Atom W update is delta equals V divided by square root of U plus epsilon, where V and U are the first and second gradient moment exponential moving averages, respectively. And then epsilon is the hyperparameter that we pick for our Atom W optimizer. So looking at what is independent weight decay, for some parameters theta, let the unscaled Atom W update equal the, let's see, what was it? The first moment divided by the square root of the second moment of the gradients plus epsilon. So we're not introducing the learning rate here. So this is the unscaled update. If we have weight decay, we have a weight decay coefficient lambda. We have some max learning rate eta, and we have some schedule from 0 to 1 that we are introducing our learning rate with. So in the original paper, they have decoupled the learning rate from the weight decay term. So they have the original parameter, or the last steps parameter, minus the scheduling step value between 0 and 1, multiplied by the learning rate times the unscaled Atom optimizer update, minus the weight decay coefficient times the parameter. And so here, eta is only being multiplied by the Atom optimizer unscaled update. It's not multiplying the weight decay value, so it's decoupled. And so this is referred to as independent decay. On the other hand, the default implementation in PyTorch is where eta, the learning rate, is now scaling both terms. So eta is pulled outside of the parentheses, and now we have the unscaled update minus the weight decay, and all of that is being multiplied by the learning rate. This is the documentation from the Optimi library by Benjamin Warner, and in his library, the fully decoupled weight decay optimizers are provided. And here in this documentation, we have gamma divided by gamma max. Gamma is the learning rate, and this fraction here is the relative learning rate, which is basically the same thing as this ST value, which is telling you basically how far along the learning rate schedule you are. And so if we look at PyTorch's Atom W, they are adding the weight decay coefficient times the parameter and then multiplying it by the learning rate. Whereas in the Optimi fully decoupled weight decay value, that term is not there. Instead, we're subtracting by this relative learning rate or schedule step and multiplying that by the weight decay coefficient times the parameter. So we're decoupling that from the learning rate itself. So let's look at our LR versus loss curves and our LR sensitivity. And we see the same trend here. I think this is a really nice chart to look at because it helps me understand like what LR sensitivity really is. So if we look at the 300 million parameter model, the blue line is independent decay is true, and the orange line is independent decay is false. And we can see that the blue line is relatively flat, right? The loss is around, 2.8 or so, 2.7, 2.8. Whereas the orange line is distinctively U-shaped. So a small change in learning rate is going to deviate from the minimum here at around 2.7. And so that again is another nice visual way to get a sense of what LR sensitivity is. LR sensitivity is basically a flat learning rate versus loss curve, low LR sensitivity. High LR sensitivity is a U-shaped loss curve, or upside down U or right side up U-shaped loss curve when we're looking at learning rate versus loss. And again, it's not as dramatic as some of the other ones, but using independent weight decay makes our training less sensitive to learning rate differences. Okay, so we looked at warm-up, we looked at independent weight decay. Now we're going to look at scaling width versus scaling depth. So what we have seen so far is that as the number of parameters increases, the learning rate sensitivity gets worse. In what gets worse means is that it gets increased. So when we increase the number of parameters, we know that learning rate sensitivity gets worse. Is it because of scaling the width that makes it worse, or is it scaling depth that makes it worse? So again, we're going to run some experiments and we're going to plot the LR versus loss curves and the LR sensitivity width versus number of parameter curves. So the blue lines here are scaling width, so we're going from a dimension of 256 to 2048. The orange lines are scaling depth, so we're going from a 3-layer model to a 96-layer model. And I think the most distinctive feature is that scaling depth increases learning rate sensitivity at a faster rate than scaling width. So what does that mean? As the number of parameters increase, if we're adding more layers, that's going to make our learning rates sensitivity get worse. So our model is not going to train unless we find, or it's not going to train as well in terms of lower final eval loss unless we find the right learning rate. If we're scaling by width, so we're getting a wider model because we have a wider MLP layer because of our hidden dimension getting larger, or intermediate dimension getting larger, it's still going to increase, but it's going to increase at a slower rate. So we have a better chance of finding multiple learning rates where we can still get relatively low loss. And again, we can kind of see the 2048 dimension learning rate versus loss curve is relatively flat. Whereas if we look at the 96 layer loss curve versus learning rate, it has more of this U shape. Okay, one more experiment they did about scaling width versus depth is they combined depth and width and did joint scaling. And they found that when you do joint scaling, you achieve a lower loss than scaling depth and width independently. And they removed QK-layernorm, which was the default in all experiments. And they removed QK-layernorm, and what we find, and it'll be a little easier if we look at this chart here. So the range of learning rates here, we go from about, 3 to the times 10 to the negative 4 to 3 e neg 1. So we're going 3 orders of magnitude here, and we still have, some stability, a lot of stability. If we remove QK-layernorm, we can now only go from 3 e neg 4 to 1 e neg 2. So we have about half of the range is now possible, because if we go past that and try a higher learning rate, we're going to diverge our loss. I have not included the mu param analysis because this was something that would have taken me a lot longer to understand, and I'm keeping that out of scope for now. But I did find this really nice blog post by Cerebrus AI called The Practitioner's Guide to the Maximal Update Parameterization. And they say that its adoption is limited because of its complexity and the challenges in implementation. And so they're trying to kind of lower that barrier. And they show that by using mu parameter or mu param, you can achieve stable hyperparameters across model scales, reduce the need for costly tuning, and improve training stability at large scale. So definitely something relevant, but it was not something I felt comfortable presenting on because I need to spend more time understanding it. All right, so there's some additional experiments that they run. They try a different number of training steps, and they find that it does not meaningfully change the LR sensitivity. In some cases, the order of magnitude of learning rate sensitivity was 2 orders of magnitude, so 100 times, higher or lower. When they change their training steps, you're only seeing a learning rate sensitivity change by, 2, I guess at most 2, maybe a little more than 2 times. So 50 times less variability than what we saw with some of these other instabilities and mitigations. They also applied the normalization of the QK layers across the head dimension versus the model dimension, and they found that the across the head dimension gives them a lower loss for each model size, and so that's the default they chose. They also tried to change the batch size from 256 to 1024, and again they found that this is not really doing anything for learning rate sensitivity. These curves are pretty much the same. However, they did see that when they don't apply QK-layernorm, batch size does start to play a difference. It starts to kick in, especially at larger model sizes. Here they tried different values of weight decay. And again, it's not insignificant in this case. There's 1 order of magnitude difference in the learning rate, but it's not as significant as some of the other ones that we've seen. For example, again, QK-layernorm not being involved, we see a lot more instability, especially at higher learning rates. And we see that the range of learning rates that provide a stable training and a low loss is much narrower than when you do have QK-layernorm. All right, so the next thing they did is they wanted to see if all of these experiments that they're doing on these relatively small models, can we predict large-scale model instabilities based on this information? So using the attention logit growth instability as an example, we show that it is possible to predict an instability before it emerges. So on the y-axis, we have the maximum attention logit. So it goes from 100, 10,000 up to 1 million. Each chart from left to right has an increasing learning rate associated with it. And then on the x-axis, we have the number of parameters, so the model size, from 10 million up to 1 billion parameters plus. The line here is at 10,000, which we're going to see is significant in a second. The blue lines and blue marks are for situations where QK-layernorm is true. The green marks are for situations where QK-layernorm is not implemented. Circles indicate successful training runs, whereas X's indicate failed training runs, so you have exploding loss. The solid lines are quadratic fits to the points that have been experimented on. The dashed line are the extrapolated trends based on those quadratic fits. And then they actually did an additional experiment at a large scale, relatively speaking, to validate the predicted instability. So obviously a lot to unpack. Let's start with what we do know is that QK-layernorm does help. And if we look at every single one of these learning rates, right, from 0.0001 up to 0.1, the with QK-layernorm line for max attention logit is pretty much flat. So what we're seeing is stable, consistent, not exploding, not collapsing attention outputs. As soon as we go to a QK-layernorm being false and the learning rate starts increasing, so it goes from, 1e-4 to 1e-2, now we start seeing the exploding attention logits. And if we extrapolate this to, I think this was a 4 or 5 billion parameter model, we can see that it crosses this 10 to the 4 threshold. So one question that was unresolved, actually one more thing I want to go back on, is that this extrapolated line was confirmed by this additional experiment where they actually tested a 4.9 or whatever 5 billion parameter model, and they actually confirmed that the max attention logit, is 10 to the 5. And so this validates their extrapolation. Okay, one question unresolved by this analysis so far is whether we could have predicted that instability arises when the max attention logit exceeds 1e4. So I think, another way of thinking about this is there anything special about this 10,000 value? So what they did is they transplanted different values of max attention logit into a small network with 10 million parameters. For different constants kappa, we pass the queries and key through this function where it basically normalizes the query or key value, the input, and then it sets the magnitude of that or is the magnitude of the RMS to square root over k, and before they compute the attention logits. So they're kind of forcing this value, because q and k get multiplied by each other, you're going to have, square root of k times square root of k, so you're kind of forcing the attention logit values. So loss deteriorates around, or not k, kappa, loss deteriorates around kappa of 1,000. And by kappa of 10,000, the loss exceeds that of a 0-layer bigram model consisting of the transformer we use without any self-attention or MLP layers. So here is their kind of ablation. They scale this constant kappa. This dotted line is their zero layer model baseline for loss. And when you hit this 10,000 value for attention logit is when you cross this, baseline loss and you get worse than that. So there is something about this value of 10,000 that seems to be the threshold for this instability. I'll walk through a couple of explanations that Claude provided. So this G of Z formula that they have is an elegant application of normalization with controlled scaling. So dividing Z by the RMS of Z normalizes it to having a unit RMS, and then multiplying by square root of kappa rescales the normalized vector to have an RMS of exactly square root of kappa. The beauty of this approach is that it preserves the directional properties of Z while precisely controlling its magnitude. This allows the researchers to systematically investigate how the scale of attention logits affects model performance without changing the fundamental patterns in the data or the model architecture. So you're still training on real data, you're still training with a real transformer architecture, you're still even keeping the directional properties of these vectors, but now you're kind of forcing and controlling its magnitude. Okay, so last couple sections here, we've looked at now kind of full circle. These instabilities exist at small scale. The mitigations also exist at small scale, and we can predict when the large scale instability will happen, right? At what learning rate? So if we go back here, at what learning rate are we going to experience maximum attention logit divergence for a 5 billion parameter model? We know the answer is 0.01, right? So if we don't apply QK-layernorm, we can't go past, 0.003, 0.005, etc. So we've done all that kind of full circle in terms of what's already known to be a problem, what's already known to be other interventions like warmup, like weight decay, decoupling from the learning rate. This next section is about identifying new instabilities based on different things they observed in their experiments. So they want to search for instabilities that are currently not well documented. Our investigation shows that gradient norms decrease with both scale and learning rate, such that the default Adam W epsilon hyperparameter is too large. This causes updates that are too small. We connect this phenomenon and the attention logit growth instability to parameter norm growth. And so parameter norm growth is basically saying the weights of the model, the norm of the weights of the model are growing. That's causing this gradient norm to decrease, and that's also causing the attention logit growth to happen. And we'll look at their kind of hypothesis and explanation in a bit. So this is what we're looking at here in terms of their gradient RMS. So on the y-axis, we have gradient RMS, which goes from 10 to the negative 4 down to 10 to the negative 8. And I've highlighted 10 to the negative 8 because that's the default Adam W epsilon hyperparameter value. As the number of parameters increases, the gradient RMS drops. As the learning rate increases, so we go from blue to magenta, the gradient RMS collapses. Again, we see learning rate here and number of params here, same thing. Here is the block index, so as we go deeper in the model, we also see that the gradient RMS drops. And that ties back to residual connections, kind of compounding the input norm as you go through the model. And at the end of the transformer layer, after you do your layer normalization, you divide by I believe it's the norm of the input. And because that residual connection makes that input norm large, the gradient, the deeper you go, is smaller. So just a couple points I wanted to highlight from my conversation with Claude. This trend is concerning because as models get larger and use higher learning rates, the gradient RMS approaches the default Adam W epsilon hyperparameter value of 1e-8. This is problematic because in the Adam W optimizer, the update is calculated as delta equals the first moment, the exponential moving average of the first moment, divided by the moving average of the square root of the second moment plus epsilon. When the gradient RMS becomes comparable to epsilon, the denominator becomes dominated by epsilon, and your numerator, which is the moving average, also decreases. So your numerator decreases, square root of a already small value decreases, and as it gets closer to epsilon, you're basically decreasing the numerator without significantly increasing the denominator, so your unscaled update gets smaller and smaller. And when your unscaled update gets smaller, you multiply it by the learning rate, the actual update to the parameter gets smaller, and you're failing to learn. You're stopping your learning. This is pretty much the same information that they provided in the textbook. I don't think there's anything I wanted to highlight other than saying that, yeah, if the gradient RMS is on the same order as epsilon, then the unscaled update will decrease in magnitude. The parameters will not receive learning signals as intended. And so let's take a minute to kind of decipher this chart. We have 3 rows of charts. We have unscaled update RMS at the bottom. We have the gradient RMS in the middle, and we have the loss at the top. The 4 columns each correspond to learning rate. It increases from 3e-4 to 3e-1. And then the lines, the color of the lines goes from cyan, which is a 9 million parameter model. It goes up to 1 billion parameter, which is the magenta. And I think the most distinctive one is here where we have a large learning rate. A couple of things I think are interesting. First of all, we see that the unscaled update collapses. It drops, 1 or 2 orders of magnitude as we go from step 0 to 25,000 to 50,000. When we look at the loss curve, we see that the loss actually gets worse, and it spikes a couple times and is relatively unstable until it passes this 50,000 step threshold, after which the unscaled update also kind of comes back up, but doesn't really reach the original. Well, I guess it kind of does. It's a bit hard to tell there. And the gradient RMS is collapsing down to 10e-8, which is the default epsilon value in our AtomW optimizer. So my understanding from this is a little, I guess, fuzzy. I think, the clearest signal I'm seeing from this chart is that the loss gets worse. So I think that is related to this giant dip in the unscaled update. So the loss getting worse is indicating that the model is not learning. Now, why does it get back up to normal? I'm not really sure. Does this mean that if this collapse didn't happen, would we have seen a much lower loss here? Would it have looked something like this, right? So if we look at point, we see that the unscaled update drops, but it doesn't collapse as much. And we see that the loss, goes down to, what is this, 3.0? So, there's almost like a 25% drop in loss that we're not seeing in this regime from 0 to 50,000 steps because the unscaled update is so low. And we see, it's a little hard to tell, but it seems like this loss is a bit better than this one, or at least is not worse. And we see that the unscaled update RMS is pretty constant. So yeah, I think I'm interpreting this chart correctly. My understanding is that what we're losing with the large learning rate, what we're losing here is faster convergence and a lower loss, and we're losing that because of our collapsing unscaled update, which is happening because of our collapsing gradient RMS, because as we go closer to the epsilon value, the numerator keeps getting smaller and the denominator stays constant. A quick recap of the AtomW optimization process. First, the gradients are computed through backpropagation. Then they're used to update the first moment moving average and the second moment moving average. Then we calculate the unscaled update, and then we multiply by the learning rate / the weight decay, depending on whether or not we're using that, and we get the actual parameter update. So what is the mitigation for this issue? And it's very straightforward. An obvious mitigation for this issue is to simply lower the AtomW epsilon hyperparameter from its default of 1e-8. So they cut it in almost half So now we have more room for our gradient RMS to fluctuate. And they also increase it, and they show that that makes it worse. So these two charts are showing the benefit of going from purple, which is 1 e neg 8, to blue, which is 1 e neg 15. So we get a benefit of having lower loss. And then we get the real benefit here, or I guess the related benefit, is that as we go through the block index, the gradient RMS stays within a couple of orders of magnitude. Whereas for our 1 e neg 8, the gradient RMS spanned across 5 orders of magnitude. And if we go back to this chart here, we can see that for larger models, the gradient RMS was collapsing as we went down throughout the block index. And if we go down here again, we have some more stability because of now our epsilon value is 10 to the negative 15. So our gradient RMS can decrease, 5 or 7 orders of magnitude more before it reaches that floor. On the flip side of things, what happens when you raise the atom W epsilon hyperparameter to 1 e neg 6? Well, the exact opposite happens. The gradient RMS collapses and then spikes up again, and the loss is going down, but then it explodes and our training fails. I will say it's interesting here that we have this spike in the RMS of the gradient. I would expect it to collapse, but yeah, not sure what's going on there. And if we look at our largest scale model and our largest learning rate, and we compare 1 e neg 6 in pink, 1 e neg 8 in periwinkle or lavender or purple, and 1 e neg 15 in our light blue cyan, we see this trend across the different blocks in the transformer. And we're looking at gradient RMS. So in each case, the blue line is relatively stable compared to, especially the deeper you go in the transformer compared to 1 e neg 8, and especially compared to 1 e neg 6. The unscaled update RMS is also very consistent, relatively speaking. At block 22, both of the other epsilon values have collapsed 2 orders of magnitude. Whereas for 1 e neg 15, as our epsilon value, we're still learning, right? So we're still making significant or useful parameter updates. All right, I'll end with a few other analyses that they covered. And the first one is rather foundational, even though it's a hypothesis. But I'm not going to go back to that slide. But when we were looking at the QK-layernorm, we were looking at the weights times. Well, let me see if it's not too much of a hassle to go back, because I would like to see that. Yeah. So if we go back here. Here's our parameter, right? The weight matrix, that's our parameter, or some of our parameters. So here's the weight matrix of Q. Here's the weight matrix of K. We are multiplying that by the inputs X and the input X. So the parameter norm, if the parameter norm is high, and then we multiply X times weight query with X times weight key transposed, the resulting attention logit is also going to be high. So that's kind of how I understood this hypothesis. Apologies for the blurry skipping of slides. But we believe, so this hypothesis, that the attention output logits are the first to become large because they are the only feature in the network we test whose magnitude depends quadratically on parameter RMS. For inputs X with unit RMS, a typical matrix multiply XW with parameters W will result in features Y, where RMS Y is a linear function of RMS W. On the other hand, the attention logit entries are computed via the dot product, so you're multiplying 2 sets of matrix multiplications, so it depends quadratically on the root mean squared of the weight. So we are compounding the parameter norm. So if the parameter norm is high, the quadratic result is going to be even higher. And since the attention mechanism is the only place where the quadratic dependence on parameters takes place, that's why we're seeing the instability happen there first. Now, the other place where we see instability is the output logits, and that's happening for related but different reasons. So there is an output layer norm layer after the last transformer block and before the final linear layer. The gradient from this output layer norm layer is scaled by the reciprocal of the input RMS. This RMS is growing with depth because of the residual connections. As the RMS leaving the last transformer block grows, the gradient received shrinks. So the gradient is scaled by this reciprocal. So as the residual connections increase the input RMS, and as you're dividing the gradient by this increasing value, the gradient is going to shrink, and that's going to cause the gradient RMS issue to occur. And additionally, I don't think they, let me just double check. Yeah, so the gradient receives, yeah, so the residual connection, from my understanding, my reading of this, is causing the output logits to grow. And because we're dividing the gradient by the RMS of the output logit, or of the input RMS, and because that's growing with residual connections, the gradient is collapsing. So I think there's kind of two things at play. This is kind of related to the gradient RMS Adam W issue that we were looking at, and it's also related to the output logits exploding issue that we were looking at. So that's my read of this parameter norm growth. Here is some kind of supporting evidence. RMS increases deeper in the transformer because of the residual connections, which is shown for very high learning rates that we see on the right. So here we have the RMS increasing because of these residual connections. The first two plots are for block index 2, and RMS is averaged over the final da-da-da, and then recall this. So again, my understanding of this is that the parameter norm is compounding as it goes through residual connections, and that's why we have these output RMS values that are larger. Something else that is going back to the query key layer norm conversation, which was mitigating the attention logit explosion. This was a very interesting chart. If you look at these two top right charts here, so x-axis is our training step, the y-axis here is the maximum attention logit, the y-axis here is the mean query norm. So in other words, it's our parameter norm. The attention logit curve is exactly the same in shape as the parameter norm. And I think that right there certainly shows correlation and, potentially could show causation. They also try some other experiments that we'll just run through very quickly. They try different attention scaling approaches. So instead of dividing by square root of the head dimension, they divide by the head dimension itself. And when QK-layernorm equals true, it does not have too much of a visible difference, other than you can see that for large parameter models, you get a lower loss when you're dividing by square root of the head dimension. They scale the LR by the RMS. And something that I observed in this chart, I guess a couple things. Number one, if you look at the scale LR by RMS, everything kind of looks shifted to the right. So the lowest values of loss for the standard unscaled learning rate are lower, at lower learning rates. Whereas when you scale the LR by RMS, you can go to a higher learning rate. So I think that was interesting, but it also kind of makes sense because you are dividing by some value. And then they wanted to see if the attention logit growth happens even if you're not using softmax. In other words, is softmax what's causing this? And the answer is no, because they see very similar behavior between softmax attention and pointwise attention. Pointwise attention is they replace softmax with a squared ReLU, and you basically get the same curves when QK-layernorm equals true. So a couple of high-level points that I want to conclude on. Obviously, there's a lot of information in this paper, and I think that's what makes it really interesting. And what makes it even more interesting is that it's approachable, it's accessible, it's readable, it makes sense. And because it's being applied at small scales, these are things we can replicate, which I think is the most exciting part of this. So I'll first go over the main takeaways, and then I'll end with kind of my two big picture points. So again, instabilities in large-scale model training are present in small-scale training. This allows for compute-friendly investigation, as we saw with the large amount of analyses that this paper provides. The attention logit growth instability is mitigated by using QK-layernorm. The output logit divergence is mitigated by using auxiliary z-loss. I'll skip down to the bottom here. Parameter norm growth is hypothesized to cause attention logit growth and gradient RMS collapse, as well as the output logit RMS, as we saw, because of the residual connections. The warmup and independent weight decay strategies are going to help us stabilize training. Scaling depth destabilizes training faster than scaling width. We can predict, importantly, large-scale instability learning rates by extrapolating small-scale performance. And the lesser-known gradient RMS collapse is mitigated by decreasing the atom W epsilon, which is something you can just is a quick parameter change when you instantiate your optimizer. So a couple of big picture ideas that I want to end with. These discoveries mean we can now predict and prevent expensive training failures before they happen. And this could, potentially save hundreds, depending on what scale of GPU you're using, thousands, maybe even more in compute costs. If you can experiment and iterate quickly, which, if you're a fast AI student, you'll definitely have heard this a lot, is like, if you can shorten that iteration loop, you can get to your answers quicker with more certainty and with more evidence. And the best way to shorten your loop is to train on smaller models. And if we can train on smaller models and we can understand how the dynamics of training are going to change at larger scales, we can avoid some of these pitfalls so we don't have to repeat, very long training runs. And then the second thing is that if you can implement these tested strategies to lower the learning rate sensitivity, you can spend less time finding the right learning rate, as multiple values will give you close enough to optimal eval loss. So this should say to lower the learning rate sensitivity. So this idea of learning rate robustness, where you kind of have these flat regions in the learning rate versus loss curves, where multiple learning rates across 2-3 orders of magnitude are giving you the same eval loss or the similar eval loss, that makes it a lot easier and a lot simpler and a lot cheaper to find a good enough learning rate that you can train with. And so I think, again, that tightens the iteration loop and that avoids compute costs, where you can spend that on doing other more interesting things. So that is a wrap for this paper summary video, something that's coming soon. I'm hoping tomorrow, if not Saturday. I have been really inspired, and it's really sparked a flame in me by participating in a tiny model hackathon where we pre-trained tiny models to generate tiny stories. That experience has really reignited my passion for small models and for tiny models. I reread the tiny stories paper, and now I've reread this small scale proxies paper, and I'm putting those two together and coming up with a project that I'm going to release, and at least announce, not release, but I'm going to announce either tomorrow or Saturday, by presenting my research plan, version 0, for this work that I'm going to do publicly, open source, the whole 9 yards. So very excited to share that. I'm super excited to work on it. It's going to be a lot of work, but I think it's going to be a lot of fun as well. And as always, I'll be, sharing everything in videos, blog posts, tweets, Blue Sky posts, etc. So thank you for watching. I hope you tune in to watch my research project launch tomorrow or Saturday, and I'll see you in the next video. Thank you.